Welcome to the Explainer. Today we are taking this incredible journey into the really meticulous, behind the scenes engineering that it takes to actually build a spacecraft. It's super easy to just look up at the night sky, right? Or watch a rocket launch and totally marvel at the final product. But that path, the path from a literal blank sheet of paper to a fully functioning satellite up in orbit, well, it's this fascinating giant puzzle of physics, logistics, and really strict methodologies. Okay, let's dive into this.
So here's our flight plan for this explainer. First up, we'll hit the mission need. Second, designing the spacecraft. Third, choosing a development model. And finally, we'll wrap up with integration and testing.
All right, section 1, the mission need, the why and the what. Before we actually look at the requirements, I really want to anchor our whole discussion with this profound quote right from our source material. It goes, "Remember, Mother Nature gets a vote and her vote counts." And wow, is that true? Space is just a relentlessly unforgiving environment. We're talking absolute vacuum, wild temperature swings, intense radiation, and these immense vibrations during launch. So every single requirement we draft, it's basically answering to Mother Nature's ultimate test. So all systems development starts with a mission need. That's the why. Then we develop the mission requirements. That's the what. But here's where the real roll-up-your-sleeves engineering actually begins. We have to translate that why and what into the how. And we do that by creating what are called derived requirements. It's like a domino effect that cascades across 3 critical segments. First, you've got the space segment. This dictates the orbit, the actual spacecraft design, and the payloads, things like communications or remote sensing gear. Second is the ground segment. That means the physical facilities, the software, and all the personnel training, right down here on Earth. And third, the launch segment and launch flow. That's the whole orchestration of actually getting us up into orbit. Honestly, this whole requirement generation process, it is highly iterative and involves just constant compromises. Moving on to section 2, designing the spacecraft. Form follows function. When you look at the overarching visual structure of the design process, you really start to see that every kind of spacecraft has some combination of these specific features. And how they're organized, well, that literally determines the entire shape of the vehicle. It's this incredibly strict hierarchy. Like I said earlier, it's a domino effect where one decision completely locks in the next one. So let's just break these boxes down step by step. Naturally, the first step is always the mission. You've got to intimately understand your destination, your duration, and the exact type and quantity of payloads you're bringing along. Like, are you observing weather patterns for 10 years? Or, I don't know, are you a short-lived probe heading way out to intercept a comet? That basic mission profile basically serves as the ultimate anchor for literally everything that follows. So the crucial point is how that mission dictates our second step, which is pointing. The specific payloads you selected will strictly determine which way the spacecraft needs to point and exactly how accurately you've got to maintain that pointing. Think about it. A high-resolution space telescope, that requires an incredibly complex, super rigid pointing system. But a basic communication relay, it kind of just needs to generally face Earth. Night and day difference, right? And once pointing is established, the third step just naturally falls right into place. Payload location. Those really strict pointing requirements we just talked about, they essentially dictate exactly where your instruments physically have to sit on the spacecraft relative to all the other equipment. Basically, your instruments get priority seating. You have to ensure they get a completely unobstructed view of whatever their target is. Which brings us to the final piece of this whole design cascade. The next absolute biggest driver is your power source, which, is typically these massive solar arrays. They take up a ton of space, but they absolutely positively cannot block the view of those precious instruments we just gave priority seating to. And because of that, all the remaining subsystems, stuff like the communication radios, the data processors, thermal controls, they're all just kind of relegated to the main bus structure. It's actually pretty interesting. Subsystem location rarely drives the overall layout of the satellite. It basically just has to fit into whatever space the payload and the power sources leave behind. Kind of like packing the trunk of a car after the big suitcases are already in. All right, section 3, choosing a development model. Building the blueprint. Before we actually look at specific models, we really need to understand this huge modern paradigm shift called concurrent development. The whole goal here is to just optimize overall time and productivity. So instead of waiting around to test a physical object, engineers now use simulation-led analysis to design out problems and validate new concepts entirely in the virtual world. They're performing product testing way ahead of time, running it concurrently with the development programs. This is a total game changer because it ensures that ridiculously expensive prototypes and tooling aren't just wasted on a flawed design. Historically, though, the gold standard has always been this serial, or the waterfall development model. And it makes sense, right? It follows this strict logical sequence that literally flows downward, from requirements to design, down to implementation, testing, and finally operation. Now, to be fair, this is generally the only way to develop massive, extremely complex systems like spacecraft, just because it allows for that full, super methodical application of systems engineering. But man, it comes with some huge risks. The biggest disadvantage? Technological obsolescence. Because it takes so incredibly long to flow all the way down that waterfall, the tech you designed way back in year 1, it might be completely outdated by the time you actually launch in year 7. No way around it. That's a tough pill to swallow. And this brilliantly illustrates the alternative we have, the spiral development model. Instead of just a single rigid straight line, it's more of an iterative cycle. It's this loop of risk analysis, prototyping, and testing that slowly grows outward. Honestly, the simplest way to think about this model is just build a little, test a little. You cycle through the concept, the design, the code, and the testing multiple times, and you're just constantly refining the product with each single loop. Now, this spiral model definitely has some very distinct advantages and drawbacks. On the good side, the entire application is built by working really closely with the user. That means any glaring gaps in the requirements, they get caught super early as you dive into more detail. But on the not-so-good side, well, it requires some serious discipline. Because the user often isn't the one responsible for the schedule or the budget, actually controlling the project scope can become incredibly difficult. Plus, it always begs the big question, exactly how many spirals are enough to finally get the product right? It can quickly become cost-prohibitive if you just keep tweaking and tweaking the product forever.
Okay, moving to section 4, integration and testing, proving it works.
Let's move to and see how this builds. Testing a spacecraft is obviously a massive challenge in systems engineering verification. So we follow a really strict sequence that builds right from the ground up. We start at the absolute smallest level, testing individual components or units, like a single transmitter or maybe a power supply. Then we integrate those smaller components into subsystems. For example, testing the entire electrical power system all together at once. And finally, we integrate all those subsystems into the main body and run end-to-end tests at the full spacecraft level. It's basically this highly methodical staircase of validation. And once we're at that full spacecraft level, we conduct functional testing just to make absolutely sure all the parts are actually talking to each other. But we also do intense environmental testing. I mean, we literally place the spacecraft in these massive thermal vacuum chambers to simulate the freezing cold, the boiling heat, and the completely airless void of orbit. We blast it with shock and vibration tests to mimic the violent shaking of a rocket launch. But here is a really fascinating challenge for you. Systems like propulsion or attitude control, you can't exactly just safely fire those off inside a lab down here on Earth. So what do? Engineers use these clever hardware-in-the-loop simulations and physical stimulators. These literally trick the spacecraft sensors, like its star trackers or sun sensors, into thinking it's actually out there flying through space. It's wild. It allows us to test its reactions while the whole thing is still safely bolted to the lab floor. Which brings us to the final thought of our explainer today. We've spent all this time talking about the cradle of spacecraft design, right? But what about the grave? Like, what actually happens to a satellite when its mission is finally over? Well, proper life cycle planning actually includes strict legal mandates for the safe disposal of these satellites, whether that means intentionally burning them up in the Earth's atmosphere or moving them way out to a safe graveyard orbit. It's just a striking reminder that managing a spacecraft goes far, far beyond just launch day, which leaves us with a pretty critical question to ponder. With literally thousands of new mega-constellation satellites launching just in this decade alone, how long is it going to be until that orbital graveyard becomes way too crowded to navigate safely?